Hey, what's up everybody? I'm your friend Inside XO. Since I don't have any specific purpose on what kind of project that I should working on, so I normally just doing things based on my interests. So today our topic is to find a way to do neural machine learning. And to be specific, we are going to do some translation program. And that program need to be using the machine learning technology. And here is to use Tensorflow because it's the only framework that I know very well. In one sentence, I don't have a choice. Well, shall we begin this journey? Neural machine translation with attention. The notebook trains a sequence-to-sequence model for Spanish to English translation. This is an advanced example that assures some knowledge of sequence-to-sequence models. After training the model in this notebook, you will be able to input a Spanish sentence such as this and return the English translation. Are you still at home? The translation quantity is reasonable for a toy example, but the generated attention plot is perhaps more interesting. That shows which part of the input sentence has a model's attention while translating. Here you can say you, at, and, or you are at home is very obvious among all those spots. At the beginning, he just from the future imported absolute import, division, print function, Unicode naturals, and he also imported the TensorFlow STF, imported the matplotlib, imported the Skyner for splitting the dataset into training dataset and test dataset. He also imported the Unicode data, the regular expression module, the NumPy library, OS/IO, and Tom. Download and prepare the dataset. We'll use a language dataset provided by this. This dataset contains language translation pairs in the format. It's very obvious. In this dataset, the data are composed by this form. Begin with an original sentence, then comes with the translated sentence. There are a variety of languages available, but we will use the English to Spanish dataset. For convenience, we have hosted a copy of this dataset on Google Cloud, but you can also download your own copy. After downloading the dataset, here are the steps we will take to prepare the data. 1. Add a start and end token to each sentence. 2. Clean the sentences by removing special characters. Why they ever want to do that? Because in their eyes, they think the special characters is not important at all. 3. Create a word indexed and reverse the word indexed. Dictionaries mapping from word ID and ID. No, word to ID and ID to word. Pad each sentence to a maximum length. No offense, but it seems like the carrots did all those jobs for us. If we want to download something, we will just need to use the tf.carrots util.get file. We gave it a field name and the downloading address. Then the library will do the rest job for us. Then we define a function which converts the Unicode file to a cycle. I don't know why they ever want to do that, because I think Unicode is a commonly used character coding format or standards. But they must get their own reasons that we didn't know. Then he just defined another function. The name of that function is preprocess sentence, and it takes a variable of w. What the w does is, no, I don't know. Maybe it's just a sentence or something like that. What I did is to take the lower character or alphabets of that, and it tries to get rid of all those spaces before and the end of that sentence. Then he did something like this. He just trying to creating a space between a word and the punctuation following it. It's something like this. He's a boy with a dot. Then it becomes he's a boy, followed by a space, the dot. I don't know why they ever want to do that. Oh yeah, we can have a look at this link. Maybe we can find out why. It is said you can use a regular expression to match the punctuation characters you are interested in and surround them by spaces. Then use a second step to collapse multiple spaces anywhere in the document. This seems not helping at all. Okay, let's leave it there. We don't have to really understand why they ever want to do that, because we don't have to. Then he just replacing everything with space except character A to Z, capital A to Z, dot, and those symbols. You can remember this regular expression for your own use, because it's quite convenient to use if you wanna replace everything with space except this. Then he just did another step to remove the additional space. Then he just added a start and an end talking at each sentence. Then he just defined two sentences, the English sentence and the Spanish sentence, for showing what the function preprocessing sentence does. For example, if the original English sentence is something like this, then after that processing, it could be end like this. Okay, we got it. Now let's move on. Then he just created another function which names create dataset. This function does three things. The step 1, remove the accents. Step 2, clean the sentences. Step 3, return word pairs in this format, English and Spanish. And this function takes two parameters. The first one is the path of that dataset field. The second one is the number of examples. We don't know why they ever want to use this, but we will know if we keep reading this. Lines equal to io.open, the path of that dataset. The encoding equal to UTF-8, that read, that strip, that split with new line. By using this line of code, we could be able to get all those sentences line by line. Alright, let's take a look at this line. So we'll take number examples, that many lines, for L in lines. And for each line of texts, we split it by using this character. Then we will get the English one and the Spanish one in one nest. We will get a lot of nests like that. Then we return the zip format of that nest. To be more specific, we will get two nests. One nest contains all those English sentences. The second nest contains all those Spanish sentences. Okay, it's easy to follow at this stage. Now we define another function. The name of that function is maxLength. We will take a length as a parameter. A length is also a tensor. Even they have different length, but they are still the same thing, trust me. So what this function does is to calculate the max length among this list. For example, if we have a list which contains a lot of sentences, by using this function, we could be able to find the longest sentences and we will return the max length of that sentence. Alright, let's go on. The next function we have defined is tokenize. Here we just used a built-in function in Keras, which name is preprocessing.text.tokenizer. It receives a parameter of filters, which I guess is nothing. I don't know what the tokenizer does, but it's fine. Let's keep reading this. Long tokenizer that fed on texts len. Tensor equal to long tokenizer dot texts to sequences. Tensor equal to tf dot keras dot preprocessing dot sequence dot pad sequences. Tensor and the padding equal to post. Then it returns the tensor and long tokenizer. I have no idea what it does, but we will know it later. Then we just defined another function, load dataset. It takes the path and the number of examples as parameters. So by using the create dataset, we will get the target language and input language. Then we feed the input language to tokenizer to get the input tensor and input language tokenizer. Then we feed the target language to tokenize function. Then we will get the target tensor and the target language tokenizer. So at this stage, we don't have to understand what the tokenizer function does. All we have to know is that if we feed the language data to it, it will return us the tensor representation of that language data and the corresponding tokenizer. Okay, that's enough for us to grab. Limit the size of dataset to experiment faster. Training on the complete dataset of greater than this number sentences will take a long time. To train it faster, we can limit the size of the dataset to this number of sentences. Of course, translation quality degrades with less data. Okay, finally, the number of examples got meaning in here. Creating training and validation sets using an 80-20 split. The sense that only matters in here is 0.2. This printing will tell you the length of input tensor training, the length of target tensor training. At least you know that it's related. They get the same number of examples or samples, whatever you call it. Then he just defined another function convert. It takes the len and tensor. For t, it tensor. If t does not equal to 0, which is the first element of that last, we print the t indexed, then the len indexed of word by giving it the in-text. So we will end up like something, it's something like this, the indexed, then the corresponding words. And the long parameter in here is related to the input language, tokenizer, I guess. As you can see, it's quite strange. Even if the whole words are in one sentence, the indexed is different. Yeah, but I don't have time to figure it out right now. Create a tf.data dataset. Buffer size equal to length of input tensor of training. The batch size equal to 64. The steps per epoch equal to the length of input tensor training divided by the batch size. Embedding dimension equal to 256. The units equal to 1024. The vocabulary input size equal to the length of input language tokenizer that word indexed plus 1. And the vocabulary target size equal to the length of target language tokenizer that word index plus 1. Then we define the dataset. It is equal to tf.data.dataset that from tensor slices. We gave it the input tensor of training and the target tensor of training. We suffer it, we recognize the position of those data by giving it the buffer size. Then we batch that dataset. What it does is to rearrange those things, split it to pieces, so we can train our model piece by piece. Then we redefine our input batch by using this. I don't know what this code does, but it just codes, buddy. You can copy and paste it. And I think all they did are the same. We don't have to worry about those details. In the end, they are data, right? Okay, finally we are getting to the encoder and decoder model. I think this is what really matters because before this part of this passage, they are nothing. They are just did a lot of steps trying to prepare the data, right? But from this point on, we're going to do some real stuff. Implement an encoder and decoder model with attention, which you can read about in the Tensorflow narrow machine translation tutorial. This example uses a more recent set of APIs. This notebook implements the attention equations from the sequence-to-sequence tutorial. The following diagram shows that each input word is assigned a weight by the attention mechanism, which is then used by the decoder to predict the next word in the sentence. The below picture and formulas are an example of attention mechanism from Luong's paper. Well, from this picture, we can see it clearly that this model takes the original sentences and it gets the attention weights. Then he just move all those weights to the target sentence, so they could be used to predict the translated sentence. The input is put through an encoder model, which gives us the encoder output of shape, pitch size, max length, hidden size, and the encoder hidden state of shape, pitch size, hidden size. We can leave those math familiar there because we don't have to really understand them. They are nothing if they cannot be translated to code. Alright, let's take a look at the encoder here. The class encoder was inherited from the tf.carols.model. And on the initiate function, we take the vocabulary size embedding dimension, encoding unites pitch size. We initialize the parent class. Then we define the pitch size encoding or encoder unites. Embedding size. It is equal to tf.carols.layers.embedding by giving the vocabulary size embedding dimensional. Then self.gru equal to tf.carols.layers.gru. And we have to give it a lot of things. Self-encoder unites. Return sequences equal to true. Return state equal to true. Recurrent initializer equal to this. Then we define two functions. The call function. It takes two parameters, x and the hidden. X equal to self.embedding. It receives the x. The output and the state equal to self.gru by giving it x. Initially state equal to hidden layer, I guess. Return the output and the state. Then we define another function, initialize hidden state. It returns the tf.zeros. We have to define the shape of that hidden layer. So we gave it the pitch size and the encoding unites. Alright, that's the class of our encoding function. Since we have already defined the encoder class, we have to use it, right? That's why we have to define it. So we get the encoder by giving it those things. And then we can say that he just get the simple sample hidden layer from the initialized hidden state. So it's nothing but a shape. So he need to get the real stuff. So he just use the encoder of example input pitch, the symbol hidden. So he just get two tensors or something like that. I don't really know. Okay, let's leave it there. I almost going crazy right now because I had a lot of things that could not be able to understand. Then he just defined the attention class or the attention layer, whatever you call it, because it is inherited from the tf.carols.layers.layer. Can we just leave it there? Because it's just too much and I was completely new to this. I haven't touched the attention layer stuff before. So whatever, after this, he just fed the simple hidden and the simple output to this layer. So he can get the attention result, the attention weights from it. Then he just define the decoder. We can also leave it there because we don't have to understand those things. All we need to do is use it. So we use the decoder class as a layer. So we get the decoder layer. Then we use this layer by giving it the sense like this. So we get the simple decoder output. Finally, we define the optimizer. I think you guys must very familiar with those techniques. Otherwise, you will not watch my video. So the optimizer, the loss function, is all basics. It's all basic. So don't bother to say it. I'll skip it. Then we come to the training process. It seems like they just use the most difficult way to do this job. I still remember when I using carrots to do this job. It doesn't have to be this complicated. All you need to do is call a function which name is fit to do that work. But here, as you can see, it's a lot of code. It seems like he just trained all those things step by step. As you can see here, step. Alright, let's leave it there. It's nothing but additional codes, I guess. You don't have to write all those stuffs by your own because he just did that for you. All you have to do is copy and paste, and that's all. So another evaluate function translate. The input is the Spanish sentence, and if that model work, it will return you an English sentence. Cool. It's work, at least in this passage, in this website, in this web page. We will probably do an experiment by our own. Yeah, of course, because we will not be able to learn anything just by reading others' article. We have to do it by our own self. We have to use our own hands, get our hands dirty. Okay? So in the next video, I'm going to make this translation model by myself. So thanks for watching. I will see you in the next video. Bye.